Hello again, everybody. Thank you for coming. I am very pleased to introduce our speaker this week. Uh, Yevgeniya Tarasova from Purdue University is going to tell us about residual intersections of determinantal ideals of 2 by n matrices. Jenna.
So hi, and thank you, Eloisa and Carrie, for the invitation. I'm excited to talk to you guys today about residual intersections of determinant ideals of 2 by n matrices. But before we can actually begin talking about those, we should define our terms. So I'm fairly certain everyone here knows what a 2 by n matrix is. And a determinantal ideal is just an ideal generated by the minors of a matrix. But what about residual intersections? What is a residual intersection? Well, residual intersections are a generalization of something called linkage. But what is linkage? Well, the history of linkage starts in algebraic geometry, where it used to be used to, for instance, classify curves in P3. So for historical reasons and for the geometers out there, I'm going to start with a geometric definition. So let's let X and Y be irreducible, closed subschemes of a scheme Z. And let's suppose the codimension of X is equal to the codimension of a Co-Macaulay scheme Z. And let's suppose the codimension of X is equal to the codimension Z of Y is equal to G. And let's make sure that X and Y are not the same scheme. Then X and Y are linked if the number of equations needed to define X as a define the union of X and Y as a subscheme of Z is at least G. So for the geometers out there, hopefully that is useful, but we're out, but this is a commutative algebra talk, so we're going to want an algebraic definition. And this is the definition I really want you to pay attention to. So if you didn't understand the geometric definition, don't worry about that. So algebraic definition. So we're going to need a setting. So we're going to assume that R is a local Co-Macaulay ring. And we're going to let I and J be R ideals. And we're going to suppose that the height of I is the same as the height of J is going to be equal to G. And we're going to suppose that alpha is an ideal generated by a regular sequence. Then I and J are linked if I is equal to alpha colon J and J is equal to alpha colon I. Now, just as a reminder, call that the definition of a colon ideal. So alpha colon I is just the set of all X in R such that X multiplies I into alpha. And we can say that I and J are geometrically linked if the height of I plus J is equal to G plus 1. Now, linkage is really cool. It has a broad variety of applications, and for instance, one of the most well-known results in terms of linkage is this 1974 result by Peskin and Sparrow. So they say that if R is a local Gorenstein ring and I and J are linked, then R mod J is Cohen-Macaulay if and only if R mod I is Cohen-Macaulay, and the canonical module of R mod I is equal to J mod alpha. So this is really neat because it tells us that if we know the Cohen-Macaulay properties of one ideal, or if we know something about one ideal, we can know the Cohen-Macaulay properties of an ideal, we can know the canonical module, and that has a broad variety of applications. And another cool thing about linkage is that we generally know the generators of a link. We can use mapping construction to, for the most part, compute the generators of a link. But we're mathematicians. We see a cool thing and we think, can we generalize it? And that is where residual intersections come in. So again, for historical reasons and for the geometers out there, we'll start with a geometric definition. So if X and Y are irreducible, closed subschemes of a Cohen-Macaulay scheme Z, and if the codimension of X is less than or equal to the codimension of Y, which is equal to S, then, and Y is not contained in X, then we can say that Y is an S residual intersection of X if the number of equations needed to define the union of X and Y as a subscheme of Z is S. And note that this is the smallest possible number of equations. But now that we're done with our geometric point of view, we'll put that aside and focus on the definition that we're using throughout the talk, the algebraic definition. So, algebraic definition. So again, we're dealing with R, which is a local Cohen-Macaulay ring. And we have I contained in R as an ideal. And we have alpha equal an ideal generated by S elements, which is properly contained in I. Then we can say that J is an S residual intersection of I if J is equal to alpha colon I and the height of J is greater than or equal to S. And we say that J is geometric if the height of I plus J is greater than or equal to S plus 1. Now it's useful to note that if R is Gorenstein, I is unmixed, S is equal to the height of I, then we get back linkage. So residual intersection truly is a generalization of linkage. Now you might be wondering, well, I have these definitions, but I don't really have a feel for what they mean. So let's just give an example of a residual intersection. So say we have an ideal generated by the maximal minors of a generic matrix. Then these ideals are residual intersections of height to perfect ideals. And this is a result of Hunicke's from a 1983 paper. Now, what this is really telling us is that we can take something really complicated, ideals generated by maximal minors of a generic matrix, and express them in terms of something simple that we understand pretty well, height to perfect ideals. So residual intersections have uses there. But we were talking earlier about, well, we want to generalize Peskin and Spirou. So can we generalize Peskin and Spirou? Well, okay. Let's suppose that R is Gorenstein. And that R mod I is Cohen-Macaulay. And that J is a residual intersection of I. It's not going to necessarily be true that R mod J is Cohen-Macaulay. And let's give a counterexample. So the ideals generated by 2x2 minors of 2 by n matrices are Cohen-Macaulay. However, the residual intersections of ideals generated by 2x2 minors of 2 by n matrices when n is greater than or equal to 4 are not Cohen-Macaulay unless they're also links. However, mathematicians don't just give up there. They're like, okay, can we add on some extra assumptions to still make it true that R mod J is Cohen-Macaulay? And in fact, yes, you can. For instance, in Hunicke's 1983 paper, he said that if I is also strongly Cohen-Macaulay, and to be strongly Cohen-Macaulay means that the Zuhl homologies are Cohen-Macaulay, and GS is a condition on the local number of generators, then R mod J is going to be Cohen-Macaulay. And there's been research done to weaken that strongly Cohen-Macaulay assumption by Herzog, Vasconcelos, and Villarreal in 1985, and by Hunicke and Ulrich in 1988. And then in 1994, Ulrich further generalized these results and found settings where one can compute the canonical module of R mod J. And that's just the tip of the iceberg. There's still currently research being done into settings where one can compute the canonical module of R mod J, further weakening that strongly Cohen-Macaulay assumption or the GS condition. And some research on how residual intersections connect to the Gorenstein properties of Riesz algebras. So it's a very broadly researched topic. And remember how earlier I mentioned that we basically know how to find the generators of a link. However, the generators of residual intersections are not as well understood. We actually only know the computation in a few special cases. For instance, in 1988, Hunicke and Ulrich found a computation for when I is a complete intersection. In 1983, Yevgeniya found a computation for I is a height 2 perfect ideal. In 1991, Kusten and Ulrich found a computation for when R mod I is Gorenstein, and the height of I is 3. In 1992, Kusten, Miller, Ulrich found a computation for certain height I plus 1 residual intersections, and keep this in the back of your mind because we'll be referencing this result later. And then also in 2019, among their more general results, Boca and Hassanzadeh found a computation for when I is an almost complete intersection. And some of you might have actually heard me give this talk, but I currently have a preprint that says under suitable technical assumptions, if S is greater than or equal to the number of generators of I minus 2, then we can express S residual intersections of I in terms of mu I minus 2 residual intersections. So we take really potentially very big, complicated residual intersections and break them down into smaller, more comprehensible ones. And in fact, very interestingly, that if the number of generators of I is less than or equal to the height of I plus 3, then residual intersections for all S can be expressed in terms of links. And like I said before, we basically know how to find the generators of a link. So this basically tells us the generators. Now, these technical assumptions involve a depth condition, and this depth condition is notably not satisfied by ideals generated by 2x2 minors of 2x(n) matrices for n greater than or equal to 4. And so that's where this current project and this talk comes in. So I did promise you determinantal ideals, so let's get to that. So we need a setting. And in our setting, K is going to be a field of characteristic 0. And we're going to say n is greater than or equal to 4. And we're going to let R be a ring where it's K adjoined with x1 through xn, y1 through yn, and we localize that ring at its homogeneous maximal ideal. And we let M be a 2x(n) matrix where its first row is all the x's and its second row is all the y's. And we let I be the ideal generated by the 2x2 minors of this matrix. And we should note that the height of I is going to be equal to n minus 1. Then we have our main theorem for this talk. For any n residual intersection of I, and let's call it alpha colon I of I, we can pick generators A1 through AN of alpha such that alpha colon I is equal to the sum from I equals 1 through n of A1 skipping AI through AN colon I. Now we should note that these are links. So what we're saying is that we can write any n residual intersection of I as a sum of links. Now, how do we show this?
Can I ask a question first?
Yes, of course.
So right before you put in this main theorem, you said something about expressing residual intersections in terms of links in a previous preprint. Is this what you mean? It's going to be like a sum of links in that
Yes.
previous statement?
Yes, a sum of links plus a fitting ideal. So basically a sum of links, but you also have to tack on a fitting ideal.
Okay, great. Thank you.
No problem. All right, so how do we show that it's a sum of links? Well, we have a few steps. First, we show this for a special case. Second, we show that the n residual intersections of I specialize. Third, we use to also show we can deform from our special case to a generic n residual intersection. And 4, we profit. And what do I mean by that? Well, since we can express the generic residual intersection as a sum of links, and since we can specialize it to any residual intersection we want, which, yay! But okay, let's break down these steps and show how to do them. So let's start with introducing our special case. So we're going to need a setting and some notation. So here, K is going to be, again, a field of characteristic 0. Again, n is going to be greater than or equal to 4. We're going to let R be n choose 2. And we're going to let capital R be the ring K adjoined with x1 through xn, y1 through yn, z1 through zn. And we're going to let M be the 2 by n matrix with all the x's in the first row and all the y's in the second row. And we're going to let I be the ideal generated by the 2 minors of M. And for notational reasons, we're going to say delta ij is xi yj minus xj yi. And notice that these delta ij's are just the ij minors of M. So without loss of generality, we can say that I is generated by G1, by generating G1 through GR, which are binomials, such that G1 is equal to delta 2, 1. GI is equal to delta I plus 1, I minus 1, for I between 2 and n minus 1. Gn is equal to delta n minus 1. And then we have a matrix B, which is an R by n matrix with Z1 through Zn on the diagonal and zeros everywhere else. Then we let A1 through AN be equal to G1 through GR times B. And what this is basically saying is that AI is equal to ZI times GI. We're going to let alpha be A1 through AN and alpha I be A1 skipping AI through AN. We're going to let J be alpha colon I and JI be alpha I colon I. Now we have a little lemma here, and it's mostly proved through bean counting that J is an n-residual intersection of I. And then we have a slightly more involved lemma that is still mostly proved through bean counting, that each JI is a geometric link equal to alpha I plus the ideal generated by mi comma j. Now, I'm not going to tell you what specifically these mij's are. All you need to know is that these are square-free monomials. And in fact, everything we've been dealing with so far is square-free. And that brings us to the main theorem of this section. J is equal to the sum of I equals 1 through n ji. So J is the sum of n links. And in order to prove this, we're actually going to have to use the initial ideal of the sum of links, and let's call that J prime. And for initial ideals, we're going to need a monomial ordering. And we're going to choose reverse lexicographical ordering. And then we're going to do a very long computation. And then we're going to get a Grosvenor basis of J prime. And this Grosvenor basis is, in fact, going to tell us that the initial ideal of J prime is square-free. And now remember this, and we're going to be using this in our proof of J is equal to the sum of these n links. So proof. By the properties of colon ideals, we know that J prime is contained in J. So it's enough to show that JP is equal to J prime P for all associated primes P of J prime. And in order to show this, we're going to start with, we're going to need this M, which is an ideal generated by all the X's and all the Y's. And we're going to argue that the support of J mod J prime is contained in V of M. And just as a reminder, the support is all the prime ideals which you can localize the module at, and it won't be 0. And if this module is 0 localized as a prime, then JP is equal to J prime of P. So let's prove this. So suppose a prime ideal Q doesn't contain M. Then I localized at Q is going to be a complete intersection. And then JQ is going to be equal to JQ prime. And that follows from that paper by Custon, Miller, Ulrich in 1989. And really in that paper, they said that if I is a complete intersection, or more generally, Isaac Gorenstein ideal in the linkage class of complete intersections, then J is equal to a sum of links, and our links are compatible with the links in that paper. And then, so now that we have JQ is equal to JQ prime, it's clear that Q can't be in the support of J mod J prime. So really what we need to show is that no associated prime of J prime contains M. And this is where the square free thing is actually going to come in. So we know that the initial ideal of J prime is square free. And this implies that the initial ideal of J prime is reduced. And as a reminder, for something to be reduced, it just means it's equal to its radical. And since J, the initial ideal of J prime is reduced, and initial ideals carry over and bring over a lot of nice properties, we actually get that J prime is reduced. And this implies that the associated primes of J prime is the set of minimal primes of J prime. Okay, so since we want to show that no associated primes of J prime contain M, we only need to show that no minimal primes of J prime contain M. So suppose there does exist a minimal prime P of J prime such that M is in P. Well, one thing we should note is we know that J prime is contained in J, but J is also contained in M. And why is J contained in M? Well, here's a proof for that. Suppose that it's not. Then Jm is going to be Rm, which tells us that alpha localized at M colon I localized at M is Rm. And that's because localization commutes with colon ideals. But this then implies that alpha M is equal to Im. And we know that alpha M is generated by n elements. And so that tells us that Im is generated by n elements. However, we also know that Im is generated by n choose 2 elements, which is going to be greater than n when n is greater than or equal to 4. So that's a contradiction. So J has to be contained in M. So now we have this J prime is contained in J is contained in M. And then we're also going to use the fact that P is a min prime of J prime and that P contains M to say that, well, P then has to equal M. And since J is between J prime and M, we get that M is also a minimal prime of J. But we know that I is Cohen-Macaulay. And a result from Ulrich's paper in 1994 tells us that every height I plus 1 residual intersection of I is unmixed of height of I plus 1. Which then tells us that J must be unmixed of height n, because the height of I is n minus 1, but the height of M is 2n. So this is a contradiction. So M can't be a minimal prime of J. So in fact, no associated primes of J prime can contain M, and therefore we have our proof that J is equal to the sum of links. So we proved this for a special case. Now we want to show that I in our main setting specializes. And for this, we actually show a more general theorem. And my apologies ahead of time, this theorem is going to take a bit of setup. So we're working with R, a Noetherian local ring. And we have pi, which is a map from S to S bar, which is a surjection of local R algebras. And we also assume that the map from R to S is a local map. And we assume that the kernel of pi is generated by an S regular sequence. And then let's call that S regular sequence L. We assume that S is Gorenstein. And we assume that S bar is flat over R. And we assume that I prime is an R ideal and that the height of I prime is equal to H. And then we let I be an extension. So let me actually scroll up here so we can see everything. An extension of I prime to S. And we let alpha be an ideal properly contained in I, mu of alpha be n, and J be alpha colon I. Then we have our main theorem here. Suppose I prime is Gn, R mod I prime is Co-Macaulay. The depth of R mod I prime to the J is greater than or equal to the dim of R minus H minus J plus 1 for 1 less than or equal to J less than or equal to N minus H. And that X of R to the N plus 1, R mod I prime N minus H plus 1, R is 0. And that pi of alpha colon pi of I is an n residual intersection. Then 1 pi of j is equal to pi of alpha colon pi of I. So this is what it means to specialize. And 2, L is a regular sequence on S mod J. And the proof for this theorem is very involved and we don't really have time to get to it, so don't worry about that. But I will tell you about how this theorem applies to our main I that is generated by a 2x2 minors of a 2x n matrix. So for all n, that I is actually G2n, which is better than being Gn. That I is also Co-Macaulay. And since we're dealing with our n being equal to H plus 1, this depth condition follows from I being Co-Macaulay. So what's left is this thing with X. Now for n greater or equal to 5, the thing with X is really simple. Well, sort of. It follows from a result by Raiku, Wayman, and Witt from 2013. For n is equal to 4, we need a little more work. We actually can't get that this x is equal to 0, so we reprove it and we actually have to compute x. So we use, again, Raiku, Wayman and Witt from 2013 to make certain x zeros. And then we use a result from Aachen, Buchsbaum, Wayman in 1981 to get a linear resolution, which lets us compute the of I, which lets us compute the x we need. So with using these two things and this theorem, we have that I specializes. So we just have our last big step. We just need to deform to the generic residual intersection. So again, we're going to have to set up our setting. So K is going to be a field of characteristic 0. N is going to be greater than or equal to 4. R is going to be n choose 2. R is going to be K x1 through xn, y1 through yn, z1 through zn. And S is going to be K x1 through xn, y1 through yn, and then we're adjoining zij's where I is between 1 and R and J is between 1 and N. And again, we're going to have that 2 by n matrix with all the x's in the first row and all the y's in the second row. And we're going to say that I is the ideal generated by two minors of this matrix, and it's going to be contained in S. And again, without loss of generality, we can pick generators G1 through GR of I. And we're going to pick them in a way that's probably going to look familiar. We're going to say that G1 is delta 2, 1. GI is delta I plus 1, I minus 1 for 2 less than or equal to I less than or equal to n minus 1. And Gn is equal to delta n minus 1. And the rest of the generators can be whatever we want them to be. Generally speaking, they're just the other minors. And we're going to let B this time be Zij, which is the generic R by N matrix. And we're going to say A1 through AN is equal to G1 through Gn multiplied times B. And we're going to say alpha is A1 through AN. And we're going to say that alpha I is A1 skipping AI through AN. We're going to say that J is equal to alpha colon I, and this is a generic residual intersection from result from Unikey, and it is a residual intersection. And Ji is alpha I colon I, which is the generic link, again, a result from Unikey. And again, this is a link. And then we have pi, which is a map from S to R that sends Zii, so the diagonal, to Zi, and Zij to 0 if I doesn't equal to J. And the thing to note here is that this pi sends pi of alpha colon pi of I to that special case we had earlier. Which brings us to our main theorem for this section. J is equal to the sum of I from I equals 1 to n of Ji. So let's prove that. And this should be our final proof. So since everything is homogeneous, without loss of generality, we can localize at the homogeneous maximum ideals of R and S. So now we're in the local case. And we're going to let J prime be equal to the sum of links. Now, from the previous theorem, from section 2, the specialization theorem, we get that pi of j is equal to pi of alpha colon pi of I. And as I remarked before, this is just that special case from section 1. And then we say pi of j prime is pi of the sum of the alpha I colon I, which is equal to the sum of pi alpha I colon pi of I. And these are just the links from the special case. So really, by the special case, we get that pi of j is equal to pi of j prime. And we're almost done now. So we know that the kernel of pi is generated by a regular sequence on S. And we know that because the kernel of pi is just a bunch of z's. And so we can use the previous theorem to say that the kernel of pi is also generated by a regular sequence in S mod j. So note, j prime is contained in j, and that again follows from the properties of colon ideals. And because pi of j is equal to pi of j prime, we have that j is contained in j prime plus the kernel of pi. So j is actually equal to j prime plus the kernel of pi intersected with j, which tells us that it's equal to j prime because j intersected with j prime is just j prime, plus the kernel of pi intersected with j. And since the kernel of pi is generated by a regular sequence in S mod j, we get j prime is equal to, we get j is equal to j prime plus the kernel of pi times j. And then we can just apply Nakayama to get that j is equal to j prime. And we're done. So now we have the generic and residual intersection is equal to the specific n links. We know that we can specialize it, and the specialization commutes with both the n residual intersection and the links. And then we can get whichever n residual intersection we want in our original setting. And as Carrie asked me before, this is both my previous paper and this imply that there is a connection between residual intersections and sums of links. In fact, I've given two disjoint situations where one can express a residual intersection in terms of sum of links or sum of links plus a fitting ideal. And that makes me wonder if there is, so these are sufficient conditions. So that makes me wonder if there are necessary conditions, and that's where I would like to focus my research in the future. And thank you again, Eloisa and Carrie, for inviting me to talk.
All right, let's thank Jenna for the nice talk. Questions for Jenna? Very
So may I ask a question?
Yeah.
So can we generalize this to if alpha generate an ideal which is Grunstein rather than a complete intersection?
If alpha generates an ideal that's going, so alpha is not.
It's a regular sequence. So in this case, it generates a complete intersection, right?
Do you mean alpha generates a complete intersection or alpha colon I? Because neither of them
Not
are.
alpha colon I, because alpha is a regular sequence.
No, it's not a regular sequence.
Not a regular sequence.
No, it's I think an almost complete. Yeah, alpha is an almost complete intersection.
Oh, okay.
Because the height of I is n-1, and alpha is contained in I, and alpha is generated by n elements, and actually each n-1 subsequence of alpha is a complete intersection, but alpha itself is not a complete intersection.
I see. And the head of alpha is not the head of I in this case, right?
No, the height of alpha is the height of I.
Okay. Yeah, that
I is not a complete intersection. Alpha is not a complete intersection.
I see. Okay, thank you.
Yeah.
Thomas.
I answered my own question. It was silly.
I have one sort of broad picture question. So one of my favorite linkage tools is Hunicke and Ulrich's generic constructions, right? So if it's, has that been extended to the residual intersection situation, or?
So I think what you're talking of, no, let me think. I don't believe so, because I think I looked there when I was trying to prove this, because at first I thought this would be a very easy proof to do and not actually be as complicated as it is. And I don't think it has beyond the fact that there exists generic residual intersections, but I am not 1000% sure there.
Okay, cool.
Yeah, I guess I do have a question.
Thomas.
Right, so you have these two nice results, great, expressing residual intersections as sums of links in some cases, right? Saying you want to move forward in that. But has anybody else done some other things of that nature?
So there's Boca and Hassanzadeh, which, well, sort of that nature. They're not sums of links, but for the almost complete intersection case, so my work has a parallel result. They have a slightly different, my work, this specific work, the one with the suitable technical assumptions and S being greater than UI minus 2, is kind of parallel to their work and identical, and has an almost identical, slightly different depth conditions and the like for the almost complete intersection case. And I can actually use their work to prove I get parallel results to my work with slightly different technical assumptions, slightly different depth conditions. They're basically, the difference is they require a stronger depth condition, but I require the GS condition.
But regardless, this line of research is very recent stuff, 2019.
Yeah.
Right.
Yeah, and also that Custon-Miller-Ulrich result from 1992 is sums of links, but that's
that's right. That's the.
But that one's very specific, so it's Leachy ideal. So I have to be basically Leachy to be sums of links, and it's only, well, this is also only height I plus 1, but not exactly the same. So yeah.
Awesome, thank you.
Oh, and maybe this is not quite on the topic, but since you mentioned the Costin-Miller Ulrich paper in 1992, is there anything to do with the Costin-Miller module in that paper?
You know, I don't know that paper from to back, so I honestly can't say. I don't recall seeing something like that there, but I was mostly focused on the stuff that's connected to residual intersections, and it's been a while since I read it all the way through, so you can take a look there.
Yeah, I will. Thank you.
Yeah, sorry.
Any other questions?
I have a quick question.
Justin.
So this is a very nice calculation. And I was just wondering, do you think this also extends to just maximal minors? So like 3 by n?
So that's actually another thing I'd like to research. But for that, I need, oh God, I'm blanking on the term, but let me scroll down to what Reiko, Wayman, and Witt had these, they were related to Fabians that had these ways to get resolutions in X. Huh? Yeah, it's the way I did this was with the special case. It involved this already really complicated Grosvenor basis computation, and that wouldn't be really feasible for bigger ideals. So I am curious about that, but we'd need other methods to do that.
I see. So did you sort of do some Grosvenor basis for small n's in Macaulay too, and then sort of see a pattern? Or?
Yeah, so originally I was looking at this as some sort of either counter. So originally with my old paper, I was like, well, are these sufficient? Are these sufficient conditions also necessary? And I was looking for counter examples or something like that. And then I found that these don't really apply to my case, but hey, there are also sums of links, and that's kind of cool. Is it generally true? And that took me here.
Okay, great. Thank you.
Yeah.
All right, let's thank Jenna again.